Hi, this is Chris Iannello again, and this is part 2 of the PSPICE overview. This is using the schematic entry tool called Capture. Here's what we'll talk about. We'll go through some slides first before we get into the software. We'll do a guided tour of starting a project and how to operate the interface. We'll go through the new project wizard specifically here in the charts just to talk about that a bit, talk about drawing a schematic and the need to place a ground. Of course, all analog simulations require a ground reference, a reference 0. We'll talk through the simulation types, although that's primarily a PSPICE topic. Since we're in Capture where we set up the profile, we'll go through it. And we'll talk about library configuration, how that's done in the software, and then address some common pitfalls. The new project wizard. This is the most common initial pitfall, and we talked about this during the part 1 overview. You need to select, if you want a simulatable schematic, you need to select analog or mixed analog and digital. The other ones are for board layout, and they make sure that all the parts that are available have those sorts of templates, whereas the analog or mixed digital tries to ensure libraries that have a large number of PSPICE simulatable templates. Okay, so you select that and you name it and you click OK. Generally it asks you for a blank project or it'll ask you for some general templates to start from. And the next one, any of those work. I like to pick the analog ground one, and I'll show you that when we do it. And then up pops a blank schematic. Now, of course, here I have a schematic drawn, but just some things to point out. On the left, you have the project browser, and the DSN file has a number, the transient.dsn file there has a number of folders under it. Each one of those represents separate simulation environments. So whichever one's active is what's getting simulated, so different folders, different simulations. Moving further down, the output file, and we'll go through this, there's the netlist basically for the circuit that you have there. It won't exist until you actually click the netlist button, or if you click the actual simulate button, which takes care of netlisting for you. So that appears there. We'll look at the inside of that file in just a moment. You also have right above the outputs there's a library file and a design cache. These show the OLB files, which are symbolic libraries of each part. Shows you the symbol for each part. Moving further down, there's the include files and the model libraries. We'll definitely talk model libraries. These text files, which end, you can't see the file name there, but it's .lib. These library files are basically at the core of our PSPICE simulation, so we'll look at that, and then of course the simulation profiles. As I mentioned last time, you see across the right-hand side your drawing template, which you'll draw from. I'll also point out the simulation bar across the top horizontally with all the green buttons on it, and right above that a text box that says vPulse in it right now. That's actually a part selection option. If you know the name of your part, you can start typing it in there. It'll finish it for you. You hit enter, and then that part is attached to your cursor for placement. So that's the way I most usually place parts. But we'll talk about other options, which primarily is the part browser, which is off the right tool menu, and I'll show you that as well. Now that .NET file, as I mentioned, when you draw your schematic and you click netlist or simulate, this file gets created. And if you look, for example, the first element is L_L2, and that is an inductor. PSPICE knows that because the first letter is an L. It's connected between the nodes labeled mag and HT, and it's 1 millihenry in magnitude. And that's how kind of netlisting works, basically. There could also be other parameters like an initial condition, which is omitted there. There is no initial condition. Now, there are more complex parts, like you can see X_U3, which is generally a model. And that particular one is for the model of a PWM voltage mode controller. Now, this just shows the interconnections, and it passes parameters to it. The actual model inner workings itself is in the LIB file. This, again, just the netlist file showing the interconnections. Now, the .lib file. This file actually shows now that same PWM voltage mode part, but now shows what these individual pins map to. If you saw in the previous slide, they had that was connected between all of those nodes, 1521, 0, ERR, 9, 0, N0 1198 cents, and etc. Those are the pins. Well, those map internally to pins 1 through 5, and you can see what all of the standard parameters are for the various model parameters here. For example, the reference voltage is 2.5 volts as a default. This is the default value, but that can be overridden by the parameters that are passed to it through the netlist. Now, within this, you also see there's an additional netlist, so it's kind of like a subsystem. These libraries certainly are at the heart of the SPICE simulation that we'll do later, and we should remember that every simulatable part must have a reference in some included LIB file. Now, the part browser, again, if I select off the, let me go back here. If we go back to the drawing schematic and you look in the upper right there, you'll see on the, of course, vertically along the right, you see that the cursor icon selected, but immediately to its right looks like an integrated circuit in gray with a green circle with a plus inside of it to its right. That's the part selection tool. If you click on it, up pops this window on the right hand side, and this is the part browser. Couple important things to note. First, the parts list that you see there only shows the parts that are in the libraries that are highlighted below, which is something that used to catch me, particularly when we first moved over to Capture. So that's the only thing. And if you go do a search for a part, it'll only search the part libraries that are highlighted, so keep that in mind. Also, if you look at the part, this particular NPN transistor, if you look at that schematic symbol, and then to the right there are two little icons. One with a PSPICE logo with a P over it in a light blue, and then a layout logo which is mostly gray with some green and some pink. Those icons denote the types of template that particular part has. This particular part, a 2N5058, has a parameterized PSPICE model, and it also has a layout model. If we're going to simulate the part, it doesn't have to have the parametric model for PSPICE, but at least it has to have some PSPICE template, which effectively means there's an entry in a library file and the connections to the OLB file, which allow it to operate. So keep that in mind when you're selecting parts. Many libraries in this product do not have simulatable PSPICE templates. Okay, so now we're to the schematic that we'll simulate. We'll talk this actual circuit's workings in a subsequent tutorial on DC to DC converters, but for now this is a buck converter, a step-down converter. It's operating in continuous conduction mode, and it's open loop in that there's no closed loop or negative feedback control on the system. Instead of a MOSFET, we have an ideal switch called S1. It's made out of the part S, which is a voltage-controlled switch, very much like a MOSFET. And we have D-break, which is a somewhat idealized diode. And then an inductor, a capacitor, both 100 microhenries and microfarads respectively, and a 10 ohm load. 50 volt input voltage, we see there on the left. If we simulate that for 10 milliseconds, we see that response, which is kind of ugly when you consider that kind of overshoot. But again, this is a circuit that has no closed loop control, and in a subsequent series we'll close the loop on this guy and show how much we can improve that output response. So let's generate this schematic for the remaining part of our time. So I'll go over to the circuit simulator software, and then of course programs, cadence, and we pick capture. Capture opens up for us. We click File, New, Project. Of course, we're going to pick analog or mixed digital. We're going to call it buck_open, meaning _open loop. And I'll put that in a new directory called Part 2. Click OK. Now again, it asks you what to base the empty project on. There's a number of examples here. This is probably a good one to start with if you're using the light version of the software, because it has basically an analog ground symbol, which is something that all simulations will require. You have to tell the simulation what the zero node is. So we start with this kind of project browser, and we take a look in here, and if you'll notice, there is a schematic page, which is mostly empty, but it does include, and we'll open this fully here. It does include a schematic ground. And I will close this guy a little bit down, open this up a little bit more. And here's the project browser. It has page 1. It has a design cache, which has basically the title block and this VCC part right here, and the ground node, which is denoted as 0. In the libraries, it shows basically what all libraries these parts come from, the graphic libraries these parts come from, analog OLB, breakout OLB, source STM, and special. And it shows you where the parts, what parts are there underneath it. And there's nothing in outputs right now, you'll notice, and there is nothing in anything except for a simulation profile. So let's draw our schematic, and then we'll come back and look at what's here after we go through and draw it. So for our buck converter, we're going to need a DC to DC converter, a DC voltage source. The first step is to get back here on the schematic, and I'll show you how to select a part from place part. Place part, again, that comes up as such, and if we scroll down and look through libraries, you'll see one that says source, and you look for VDC and you find it. So we'll place our source here, and then we right click, and we have to select end mode. What this does is basically, if you don't, the part stays with your cursor in multiple places. You want to tell the system that you're done. You can hit escape, that's another option, or as I like to do, I right click and click end mode. So here's our voltage source. Another way to type VDC or get it in there is to type VDC up here in the box, hit enter, and then it's attached to your cursor. So I'll right click again, click end mode. Let's put our S switch, which is our ideal switch. I'm going to rotate that, so while it's connected to my cursor, I'll hit R and then rotate it like so. In mode, and I'm going to have a diode, so I know that's called D-break. It's in the breakout library. I'll click it here, and I'll click D-break. I'm going to turn that because that's how our schematic looked. In mode there, I'm going to do an inductor. I'm going to do a capacitor. And we'll talk about the polarities on these things later. And then the resistive load model. Put that here. I hit R to rotate it. And then we'll start wiring things up. When it's time to wire things up, what you do is you'll click this place wire icon from here, and then go through and connect things together. Let's see. I don't like that. I think I'm going to move this guy up so it's in line. Now I'm clicking and dragging there, holding on to my left mouse button. And I'm wiring this whole thing up just like the picture we saw before. Not paying too much attention to my spacing or anything like that. I can drag that around and make it work, which we'll do in just a minute. Now, as we said before, we need a ground. So we can leave this connector there and put the ground up at the top, which we could do, or we could just copy this ground symbol up, which we can do. And of course the red dot indicates they've got a connection. I'm going to delete, cut, and paste the ground symbol. I'll leave this down here. Shouldn't hurt anything. And the next thing that we need to do is talk about this voltage controlled source in this part. If I double click on this part, up props the property editor, which is a number of, basically it's a database editor that has a number of fields that may or may not have anything to do with PSPICE simulation. For example, it doesn't have a PCB footprint, it tells us, and there are a whole host of other things that it tells us. But it also has the model parameters in it. Now you can change those model parameters by clicking here and changing things around. For example, the on-state voltage is not shown, but here's the off-state voltage, the on-state resistance, the off-state resistance. I'm going to make that on-state resistance when the switch is actually closed and on 1 micro ohm. And micro in PSPICE speak, as I mentioned, is a U. And then we'll leave 1 mega ohm for R off. It's assumed to be ohms, of course. And we'll look over here at V on, which is 1 volt, and we'll leave that as it is. That's good. So now I changed that, and you notice that it doesn't show actually the resistance values. So I want to show those resistance values, at least the ones that I changed. So I'm going to go back to that parameter. I'm going to select it. Let's see, where is that guy? There's R on. I'm going to display. I right-clicked on it. I'm going to click display, both name and value. And there it is, 1 micro for R on. Now let's add the ground over here in the control voltage by cutting and pasting in Control V. And now we have to think about what are we going to do with this control pin. Now a very important part to be familiar with, it's under the source library, but I'll just type it, is V-pulse. V-pulse is the way that will generate a pulse width modulated train in DC to DC converter speak. And it's basically a gate pulse of various widths that we can apply to this threshold input, this control input, to turn this main switch on and off, which is effectively what the MOSFET does for us. And I'll put a ground over here, Control V, cutting and pasting it. And let's see, let's make something a little cleaner, and let's put this ground symbol up here, but of course we'll change the name of it to gate. And we will cut and paste that. Actually, we'll copy and paste that. And I hit R to rotate it, and then I connect. And so now we have a schematic here. Now we don't have any parameters put into our source, nor do we have parameters put into our, and I'll delete this here, nor do we have parameter values. So we know we want this to be in, let's go back to our example. We want, okay. We want 100 microhenries, 100 microfarads, and 10 ohms. And you can see that we want a period of 10 microseconds, a pulse width of 5 microseconds, so that's a 50% duty ratio. With a period like that of 10 microseconds, we can invert that for the switching frequency. Since it's a square that we're generating with this pulse, we have to give it the rise time and the fall time. We'll just make those very short at 1 nanosecond. Okay, so we know what we want to do. Let's go back. And we'll change that and make that 100 microhenries. We'll make this 100 microfarads. The farads and the henries are optional, but the 100 micro part, of course, is necessary. I go in and I make that 10 ohms by double-clicking on the value. I'm going to go in here and say that this is going to be 0 volts. Our pulse source, basically our pulse train. We're going to output 1. It needs to be 1 as a threshold. We can make it 2 or what have you. I'll just make it 1. Anything above the threshold. Time delay, we don't care about it. We'll say 0. The rise time and the fall time, you can't have an immediate change, an abrupt discontinuity. It's too hard for the simulator to handle. So we'll say 1 nanosecond here for our rise time and fall time. Our pulse width, we said, was going to be 5 microseconds, and our period would be 10 microseconds. Okay. Now, and another important parameter, of course, the input voltage. We need to give it 50 volts. So we've got our schematic laid out, D-break. Now there's the initial conditions too. Right now you'll find that our initial conditions are blank. We'll start simulating it that way, and you'll find that the simulator will solve for an initial bias point solution. It'll short inductors, open circuit capacitors, and do a calculation based on that. That's what it'll start with if we don't give it an initial condition. Now, right now, the default simulation profile, if you look on the simulation window here, is the bias point solution. If I click on this Edit Simulation Profile, you'll see that the basic simulation settings are set, and it's set to do a detailed bias point solution. Now, I'm going to go up here and go ahead and click this Run PSPICE. There are a number of things like View Simulation Results and probe markers here that we're going to look through, but not yet. Right now, I'm going to go through. You'll notice there's nothing in Outputs. If I go and click Simulate, I look over here. There's no data because it's just a bias point solution. There's no time-based solution. But if I go back, I can actually click on the voltage and the current, and it'll tell us what the bias point solution was that it solved for. Now, more importantly, though, if you look over here in the output section, you're going to see that the net list is generated. So, for example, this is the gate node, and any node that you actually name with a port will carry that. Other nodes that aren't named with some port or some other means will have some generic numbering scheme that PSPICE assigns. And it basically shows the interconnections of the circuit, including these parameters that we input through the model editor. We change that to 1 micro. Now, the model for vSwitch is 1. We've passed to the model our own variation through the model the model template here. Okay, so that was basically generating the bias point solution and looking at the net list. And once simulated, you see that there's the simulation profile right here in the model libraries. Now let's go back. Let's fall back to the simulation profile that we were working on. If I click Edit Simulation Profile, we have all the simulation types that we want. One that we might be interested in would be the transient simulation, and I will run that to 10 milliseconds. And I won't tell it when to start saving data. I'll start saving data immediately to the hard drive, and I won't set the maximum step size for now. Going back here, there's a general tab, talks about the simulation profile names that we're on. So we'll call this one transient. And then there's the analysis here. We'll use the general settings for now. The configuration files. We don't have any stimulus. These are basically inputs that you apply to special sources that you want to custom create. We don't have any of those in this schematic. The library that you need to create is this one. This nominal library basically includes all of the libraries that you saw over on the right-hand side, like ABM, analog, and the like. And then there's the includes. Now, it's important that all of the LIB files that you need for all of the parts that you've placed are included here. Here's options associated with the simulation. Now, we're going to do a lot with this box when we get to PSPICE, but suffice it to say it talks about the relative accuracy of the solution, and a lot of times, especially in power electronics, we're going to have to adjust these values. Reltol is one that will definitely change, stepping Gmin, and preorder is another one that we'll look at. Now, there's a manual things that I'm used to doing because I've been using this software for a while. The modern version of this project has an auto convergence option where it basically tweaks these for you until it gets a converging solution. And we'll talk about that when we get to PSPICE. Data collection talks about what you'll mess with. I rarely touch anything in here myself. And then in probe window, I'll often change this. Now you'll notice the default in this probe window, which is basically what does it look like when you go to simulate? Does it start showing data immediately? Does it wait until the simulation is complete? Does it show markers on all open schematics, or does it show the last plot zoomed into wherever you were? I often like to have this last plot selected myself, but it's user preference. Okay, so going back now, we have the transient time domain. It's 10 milliseconds, and we can click the simulation. And before we do that, we'll move that actually into the next part. I want to look over back at the part selection dialogues over here. If we look at the ABM part library, this is the analog behavioral modeling library, and they're math blocks. These are basically areas where you can implement mathematical blocks, including differentiators, integrators, Laplace transforms, and the like. E-table, basically limited functions, and a whole host of others. I often use gain and G-table and G-value for functions, which you'll see in a subsequent video. The analog part is, of course, your analog components. Your breakout has your breakout parts, your capacitor breakout. I generally don't use anything in here except for D-break and the transistor breakouts, you know, the MOSFET and NPN transistor breakouts. And then, of course, we use S-break a lot when we're using an ideal, when we're first starting and we're idealizing the circuit. The light version of the software has these parts here, which are actual parts, evaluation parts. Like, for example, take this 7400. It has a PSPICE model you can see from the icon, and it also has a layout model, so it has a footprint as well. Not all parts are like that, but because we have, let's go through and see if we can find some that don't have, for example, this particular diode is simulatable, but it doesn't have any footprint. And there's a number of things like that in the library. But you'll find, in fact, most of the libraries you have on your hard drive have a footprint but are not simulatable. Okay, so that's kind of all of this, and that completes our overview of capture. The next step, we'll run the simulation. Thanks for your time.